Hi, this is linear transformations, specifically matrix representations of linear transformations, and this is part 3. So we're working this transformation S defined from P sub 3 to M22. It takes in one polynomial of degree 3 and it spits out a matrix with 2 rows and 2 columns. And we're working with basis. We've done the work for two previous cases where we were using two different sets of bases. And now we're going to end this discussion by doing the same type of work for a last set of bases considered in this example. So now we're going to use f as the basis. Here f is such that the span of f is equal to p sub 3, and we're going to use this set G also as a basis for matrices with 2 rows and 2 columns. Okay, and we need to evaluate the transformation at each of the basis elements, and then we need to find the coordinates, coordinatize the results relative to G. Okay, so in doing so, we evaluate the transformation. Okay, this evaluation yields this matrix here. Okay, this matrix comes out of evaluating the transformation at that polynomial 1 plus 1x minus 1x squared plus 2x3. That gives this matrix, and then what we do is that we express this matrix, right? We want to express 2 minus 2, 2, and 4. We want to express this as a linear combination, right? And this is something that's going to look in this way: 0 times that plus 0 times the other matrix. So what we see is that in that order, the first matrix here with coefficient 2 is a matrix that has 1, minus 1, 1, and 2, and the other matrices here is minus 1, 0, 2, and 2, well, and the other matrices, right? But they don't really matter because they have 0 coefficients, and by multiplying this matrix by 2, then we obtain 2, 2, minus 2, and 4, which is what is desired. Okay, so what happens now if we evaluate at the next element of that basis for P sub 3, we obtain this matrix, and we see that a way of obtaining this matrix relative to the basis G is by using a lot of coefficients to be equal to 0. We just need a -1 for the second matrix. By evaluating the next element of that basis of P3, we obtain this matrix: 2, -2 in the first column, 1, 3 on the second column, and the coordinatization, the coordinates for these relative to the basis of G are given by 0, 0, 1, and 0, right? And then in a last case, when we evaluate this polynomial 1 plus 1x plus 0x squared plus 2x3, if we do that evaluation, we obtain the 0 matrix, and the 0 matrix would have coordinates 0, 0, 0 relative to that basis G. So all this information is summarized into a matrix. Okay, this is the matrix representation relative to F and G, and that matrix has these columns. As you can see, this is what you call a sparse matrix. It has a lot of zeros in a lot of locations of its entries. And with this, we conclude the example of recomputing matrix representations for one transformation using bases for the domain and the codomain and doing this 3 times for 3 different choices of bases, of different choices of the sets that are considered the basis of these vector spaces.